Okay, welcome to this lesson to kind of like determine the derivative of logarithm functions. You might want to freeze the screen, or if you have it on your notes, you can actually go to this site to kind of like see a visualized guided discovery on what exactly is the differentiation of a logarithms. And what we are more concerned with here is the natural logarithms. For the secondary 4 syllabus, we will focus on the natural logarithms because it's in connection with the exponential function in some sense, right? Honestly, you can convert between the exponential and the logarithm functions quite quickly just by manipulating the power and so on and so forth. And when we kind of do that, we notice that the tangent of y equals to ln x actually gives us a very unique graph, and it is in fact the reciprocal graph 1 over x, right? Quite weird, but yeah, so we're gonna kind of look at more difficult ones, right? Knowing that it's 1 over x is not really a major, big discovery, right? So we're gonna kind of use the same way as we did for exponential functions. We're gonna kind of use substitution to actually figure out what is the differentiation of y equals to ln 2x, in fact. So same thing, I'm gonna let u, looks like a w, let u be equals to 2x, and therefore we have y equals to ln u. We know that dy over du will then be 1 over u, and du over dx is simply equals to 2. And so dy over dx will simply be dy over du times du over dx. Now with that, we will have 1 over u times 2. And u is simply 1 over 2x times 2, which actually just gives us 1 over x, right? But I want to focus on how we get there. And that is actually a more important part. What we see here, okay, it's very interesting over here, is that if I put them in a fraction, right? So if I put them in a fraction, it will be 2 over 2x, right? And if we look at the top part, and the denominator. So we look at the numerator and denominator, right? The numerator is the differentiation of the denominator, right? If you differentiate 2x, you get 2. And from here, we can kind of conclude that the derivative of ln of any function, right, is simply just the differentiation of the function divided by the function, the original function itself. And from here, we can go ahead to actually kind of like differentiate all kinds of natural logarithmic functions. And over here, we have differentiation of ln 5x squared plus 7x. Not too hard, but this is simply going to be a fraction. We're going to differentiate what's inside the ln function, which is 5x squared plus 7x, and that gives us 10x plus 7. What is it divided by? Simply just the original function that you see there, 5x squared plus 7x. Okay? Over here we have something difficult. You have e to the power of y, something not something you really want to see. But what we can do is, in fact, we can apply ln to both sides of the functions. So I have ln of cosine 3x over here, and this will actually, in fact, just be y ln cosine 3x. So we want to differentiate with respect to x. This is so much easier because I want to just find dy over dx. Right, and this is simply differentiating what is inside first, which is cosine 3x. If you differentiate cosine, you get negative 3 sine 3x. Okay, where did this 3 come from? I differentiate the 3x inside. So there's a bit of like chain rule of trigo involved here, and it's divided by cosine 3x, right, the original function. Of course, you can do your magic using trigo laws. This is simply just negative 3 of tangent 3x. Pretty interesting way to find the differentiation of something that gives you tangent, right? Which actually gives us some connection actually on like, hey, how can we actually differentiate natural logarithms of trigo functions? And that's actually a topic that we explore in further mathematics. Moving on is something a little bit more difficult. I would say that this is actually a bit tricky because it involves square root and so on and so forth. One of the things in differentiation is I usually try to avoid things with square root as much as I can. And the best part about this is that this is in fact a logarithm function, right? So I'm going to write it as 3 plus x over 3 minus x, okay, to the power of negative half. And because it's a logarithmic function, I have negative half of ln 3 plus x over 3 minus x. Now, differentiating quotient rule, seems like I can just directly and differentiate quotient rule, right? Yes, we can do that. And also yes, that you're going to find some issues with it because it's going to be so complicated. Your function is already a fraction, and when you differentiate it, you are going to have you have to use quotient rule, divide and kind of differentiate this 3 plus x over 3 minus x, and so on and so forth. And so the beauty about logarithms is that you can apply logarithmic laws. And one of the logarithmic laws that you can apply is the ln of a fraction, let's say p over q. And this is simply ln p minus ln q. This is so much easier for us because I don't have to actually use quotient rule here. Of course, you could brute force use quotient rule here, not an issue. But we want to try to find ways to make things easier for ourselves. And so over here, I will have this over here. Okay, now with this is so much easier to differentiate now because it's just two separate functions, and I will literally just have half times of ln 3 minus x minus ln 3 plus x. Okay, I brought in the negative, so it's so much easier. And then when I differentiate it, which is f prime x, the half remains, and I will differentiate each of them individually. This will just give me negative 1 over 3 minus x minus, this will give me 1 over 3 plus x. Why 1? Because when you differentiate 3 plus x, it just gives you 1. Okay, so your final answer, it's actually just bring out the negative half. So actually, you bring out the negative of both, right? And you will just have 1 over 3x, 3 minus x, plus 1 over 3 plus x. So that is it for the differentiation of logarithm functions. See ya.